Hey there, astronomy students. This is Miss Ruark. This is Vodcast 2.1 on the sky. I've got a lot of information to get through, so let's go quick. All right, constellations. Constellations in ancient times were a grouping of stars that people would look at, and typically they said it was only the brightest stars, and they would name them after mythological figures and gods, and say that they represented those things. So nowadays, what they are is they're just well-defined regions in the sky. They don't matter if they have bright or not bright stars in them. It doesn't matter. It's just that big grouping in that area, that region is where those constellations are. All right, so when we look at constellations in the sky, what we would typically see if we're standing here on Earth, oops, I need my pen. If we're standing here on Earth and we look up, this is what we would see. Now they look like they're all the same, they're all on the same plane. However, they're not all on the same plane. There's some that are really close, there's some in the middle, and there's some that are really far away. Okay? When we see them all like this, we call this the projection effect. But typically, it's not like that at all. It's that they're all mixed up and there's some that are close and some that are far away. We just see them as all together because of their brightness. All right, so constellations, we need to name the brightest stars in the constellation. They're given a name by a Greek letter, and it's given to them according to their relative brightness. And then they're given a Greek letter and then the name of the constellation after it. So the brightest star in Orion is Betelgeuse, which is here, and it would be Alpha Orionis or Alpha Orion because it is the brightest star. Betelgeuse is Alpha. Okay, and then the beta is Rigel. Rigel is a beta Orion because it is the second brightest star. All right, well, we use a magnitude scale, which was first introduced by Hipparchus back in ancient Greece, and it's to tell the magnitude of the stars. First magnitude would be the brightest stars. Sixth magnitude would be the faintest stars. Okay, so we know that first magnitude stars appear to be 100 times brighter than sixth magnitude stars. And the first magnitude difference gives us a factor of 2.512 in apparent brightness. Well, that's important, okay? Because remember, the larger the magnitude, the fainter the object. All right, so here we look at Orion again, okay? Here we have Betelgeuse with a magnitude of 0.41 and Rigel with a magnitude of 0.14. So to find the difference in the magnitude, we would take 0.41 minus 0.14, and that gives us 0.27. Well, we would use that as our exponent on this intensity ratio to figure out, or on the magnitude difference to figure out the intensity ratio between those two stars, and this intensity ratio would be 1.28. Here's a scale that shows us the apparent magnitude of different objects. You notice that it goes from negative numbers to positive numbers. The smaller the number, the brighter the object. The bigger the number, the fainter the object. So if you see the sun here is pretty bright because it's at like a negative 26.5. The full moon is at a negative 12.5. It's pretty bright on full moon. Sirius is the brightest star in the sky, and it's at a negative 1.42. All right, the celestial sphere is this orb that's around the Earth, and it includes the sun and the stars and the planets and the moon, and it is well, it's the celestial sphere, right? It's the sphere of the heavens. All right, of the sky. Okay, so on the celestial sphere, you have zenith, which is the point that's directly above your head. That does not mean it's north. It's just directly above your head. You have nadir, which is directly below you. It's on the other side of the Earth, straight below us, just goes straight through the Earth. And it's not visible. You can't see it because, well, you got a lot of Earth in between you and it, right? All right, the celestial equator is the projection of the Earth's equator onto the celestial sphere. So if we were to take this and put lasers and shoot them out, we would see this nice long celestial equator. Okay, and then we have the North Celestial Pole, which is a projection of the North Pole onto the celestial sphere. All right, from geographic latitude, you can see the North Pole is L degrees above the northern horizon. So if you are North Pole is up this way, the horizon is here. L would be the degrees of difference. Okay. We also know that from the south, the horizon on the south the difference here would be L as well. And then to find the celestial equator, it would be 90 degrees minus that L here. If you were, well, okay, let's change back. If you were standing here to find the south celestial pole, you would take the equator and minus it. Okay. The north celestial pole, if we're at a latitude of 90 degrees, would be straight above us at zenith. If we were at a latitude of 30 degrees, it would be slanted. Okay, if we were at a latitude of 0, it would be directly to the side. And if we were latitude at a negative 30, it would actually be down below the equator at 30 degrees, and the south celestial pole would be up. All right, apparent motion of the celestial sphere. Because the Earth's axis is tilted, it's slanted. Instead of being straight up and down, it's slanted. When this goes around and around, all you see is this object going around and around and around. And so you would, looking straight up at the north celestial pole, all of the stars, the constellations, would appear to be going around in a counterclockwise motion. Counterclockwise, if you're looking north. All right, well, if you were looking to the east, the objects would seem to be going from the horizon and up, slanted at what looks like about a 45-degree angle, but I'm sure it's slightly off from that. All right, well, if you were looking south, everything would appear to be going in a clockwise fashion instead of counterclockwise. All right, precession. Here we have a top, and this top here, you know, you've played with them before as kids. After they stop spinning really fast, they kind of tilt to the side, and then they have this wobble here. Well, that's precession. Okay, so the sun does the same thing to the earth, and it kind of tilts the sun, and it wobbles around its axis. You know, you guys say wobble, 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 wobble. Wobble, baby, wobble, baby, wobble. Yeah, okay, you know what I'm talking about. Okay, so, sorry, that song just stuck in my head. Okay, so it is wobbling around its axis here, and that's what we would call precession. And this precession takes about 26,000 years to go all the way around full cycle one time. Okay, so what does that mean? Well, as a result of the precession, every 26,000 years, the Earth, the celestial North Pole, points near one of these stars. So at about, well, here it is. At about 2100 AD will be close to Polaris. At about 14,000 AD will be close to Vega. 26,000, it'll come right back around here again. All right, the sun and the way that, well, its motions, but it's not moving. So the Earth rotating is what causes the day-night cycle. Okay, so due to the Earth's revolution around the sun appears to move through the constellations of the zodiac. All right, so if we're here on Earth, it looks like the sun's going around us, but actually it's not. We're going around the sun, and the sun is in Capricorn. So if we're here, the sun is in Aquarius. If we are here, the sun is in Pisces or Aries. Okay, so because we're moving, it looks like the sun is moving. And the sun's apparent path, or what we say it's moving, is called an ecliptic. All right, the seasons are caused because of that rotation of the Earth's axis when it's tilted, and because it's tilted this way, when the sun hits us, it only hits certain parts of the planet, and that's what causes the seasons. So it's caused by this, what we call an angle of incidence by the sun's rays. So light comes in from the sun, and here we go, and it hits the northern hemisphere because the northern hemisphere is tilted towards the sun, and so we call it a steep incidence, so it would be summer. Here it's a shallow incidence, and we would call that winter. Okay, now the light that's coming from the sun and the fact that it's tilted, that the Earth is tilted, is not related to the Earth's distance from the sun. Okay, the Earth is slightly closer to the sun in the winter that we have than it is in the summer that we have, so don't relate those two. Okay, here it's showing the difference between the northern and northern and southern hemispheres. In the northern hemisphere we have summer, and in the southern hemisphere they have winter. Why? Because we get more light here, they get less light here. Okay, well, in the northern hemisphere we have winter, and in the summer we have summer because less light here, more light here. All right, and then the Earth's distance from the sun has only a minor influence on seasonal temperature variations. It doesn't matter. Honestly, it doesn't play that big of a role. Okay, motion of the planets. So the planets are orbiting the sun almost exactly in the plane of the ecliptic. Okay, and guess what? The moon is orbiting the Earth in almost the same exact ecliptic plane. All right, motion of the planets. So outer planets, Mars, Jupiter, Saturn, Uranus, Uranus, they all generally appear to move eastward along the ecliptic. And then the inner planets, Mercury and Venus, they can't really be seen from angular distances, which means that you can't see them at any time besides morning and evening hours, or as morning and evening stars. All right, Mercury, if we look at it, it's about 28 degrees from the sun, and it can be seen shortly after sunset in the west or shortly before sunrise in the east. Shortly. Okay, Mercury here. Right? Well, guess what? Venus is about 46 degrees from the sun, and it can be seen for a few hours after sunset, and it can be seen for a few hours before sunrise. Okay, so factors that affect the climate here. The eccentricity of the Earth's orbit around the sun. Remember, eccentricity means deviation from normal. So the more ecliptic or elliptical the path or the orbit is, the more eccentric it is. Okay, so if it was a circle, it wouldn't be very eccentric. This would be an eccentric path because it's not close to that. It's more of an oval shape. Okay, precession, the time it takes that celestial North Pole to go all the way around, and then the inclination of the Earth's axis, meaning that it's tilted. Okay, so we have this hypothesis, and I'm not even going to say it because I know I'll destroy it, but the hypothesis says that changes in all three of these aspects are responsible for long-term global climate change, which are the ice ages. We've heard of that before. Yeah, you've seen all three movies, four maybe. All right, and here you go. All right, I'll see you in class.